All right, so we're in this chapter on exergy. What is this, our fourth lecture? We talked about the property of exergy. We talked about applying exergy to closed system, open system. So, and we last time talked about the exergetic efficiency. This very last section of the chapter, students like to see this word, skip. What's that mean? There's no questions on the exam on thermoeconomics using exergy. All right. Also, I have something else covered up down here. What's one of the themes as you look toward the first exam, which is next week, Monday? It's just going to be on this chapter. But guess what? You have to be able to do energy and entropy before you can do exergy. The next exam will probably be 2/3 Thermo 1 review. Just like every problem in this chapter, it's about 2/3 review of first law, second law. And then finally there's some exergy at the end. I think I've stressed that before, but make sure that you're able to solve problems. So this is where we were last time. We talked about fluid flowing through a turbine. The turbine typically is well insulated. The purpose is to extract some energy out of that fluid stream and convert it into work. Well, we can get a second law or exergetic efficiency based on the flow exergy in and the flow exergy out. So the energy, the available energy or the exergy comes out of the fluid stream and goes into the shaft. And so you can think of where does it come from? And then where does it go? Not all of it goes there. Some of it's destroyed. And that will be the basic definition of the second law efficiency for a turbine. Same thing for a compressor. It's just turned around. This is negative. You want to put it into the fluid stream. Here, the exiting flow exergy is greater than the entering flow exergy for a fluid going through a compressor or a pump. And so how much of this gets into the fluid? That gives us the definition of the exergy. All right, let's move on. We talked about the heat exchanger. We have the hot fluid flowing through the heat exchanger. We have the cold fluid flowing through the heat exchanger. There's a heat transfer, Q dot, from the hot to the cold. We also have a transfer of the exergy. Something comes out. So typically the flow exergy of the fluid exiting at 2 is less than the flow exergy coming in at 1 of the hot fluid. Something came out of the hot fluid. Heat did, as well as exergy did. And EF4 is greater than EF3, meaning it was added to the cold fluid, but was everything that came out of the hot added to the cold? Well, heat transfer, yes it was, but not exergy. Some was destroyed because of irreversibilities. So when you look at that ratio, it's out of the hot. That would be the mass flow rate of the hot fluid times EF1 minus EF2. And then what went in, I want it to go as much as possible into the cold fluid, M dot cold, EF4 minus EF3. There's our definition of the exergy. Hopefully it makes sense to you. Hopefully you can talk through the equations. Likewise, if you have a heat exchanger where you have mixing, so it's what they call a direct contact heat exchanger. So you have fluid that's a hot, it comes out lukewarm. The cold comes out lukewarm, so the temperature of the exiting stream is just one temperature. At state 3, 1 flow exergy. So again, it's out of the hot and into that other stream. What came out of the hot? The mass flow rate, 1 times EF1 minus EF3. And how much of it went into the cold? M dot 2, this is M dot 2 right there. EF3 minus EF1. So there you go. Make sense? This is 2 right there. Thank you. Fixed it. Thank you very much. You're on your toes today. You're alert. True? All right. Let's press forward. Solve a problem. that takes us a while just to read the problem. So air enters the counterflow heat exchanger operating at steady state. So the air enters at a temperature of 67 C at a pressure of 0.3 megapascal, and the air exits at a temperature of 42 degrees C. That's all one sentence. You have to probably read every sentence in the problem statement 3 or 4 times over to get it. All right, so you might want to make a sketch, heat exchanger. You think, is this air, is that going to be the hot fluid? The other fluid you're looking ahead is refrigerant 134A. So air is either the hot fluid or the cold fluid. So look at the first sentence of the problem statement. Is air the hot fluid or the cold fluid? And why? It comes out at a lower temperature. There was a heat transfer out of it. The only way for that to work is if it's the hot fluid. The transfer is going to go always from hot to cold. So there you go. So this will be the air side, which is hot. And we'll come in and go out. Maybe we say this is in at 1, out at 2. They give us the temperature. I don't have a lot of room on this page, but I would organize all that information in my schematic. And the pressure. Now let's read. So we have refrigerant 134A. Let's put that down here, refrigerant 134A. It's also going to be the cold fluid. You can deduce that. And it's a counterflow arrangement, so we have it in at state 3, and then it goes out at state 4. Okay. The refrigerant enters at a given pressure, 0.7 megapascal, and a quality of 50%. All right. And it also has a mass flow rate of 30 kilograms per hour. So we know the mass flow rate of the cold, 30 kilograms per hour. We know the pressure, not the temperature coming in. But could you tell me the temperature at state 3? How would you get that temperature? Just look at the problem statement. Was there a way to get the temperature at state 3? So this information that it's the quality is 0.5 tells us a lot. What does it tell us about the fluid state of the refrigerant coming in? It's a mixture of liquid vapor and equilibrium. And so what is the temperature of it coming in? The saturation temperature, Tsat. So T3 is equal to Tsat of refrigerant 134A at that pressure coming in. And if you have your little appendix, we could look that up right now. How many people have the appendix with the properties? So let's get to the right table, refrigerant 134A. Let's get to what table is the best table to be in? A11. Exactly, A11. We look down. Oh no, they give us the pressure in bar. But this pressure is 0.7 megapascal. So what is the pressure at 3? 7 bar. Good. So we look at 7 bar. What's the temperature of the fluid? 26.7. So this is 26.7 degrees C. All right. Now, also that quality. I asked this question. I'm going to pause. I'm going to walk around. I'm going to get your answers written on your sheet of paper. Quality means something. What does it actually mean? Do you remember the definition of the quality? Can you give me the equation or an equation or write out what it is for equality? Oh, don't call it out. I want to see if your fellow students know as well. So the reason I paused and walked around is some people will say the quality is the volume of vapor divided by the volume of vapor plus volume of liquid. Is that correct? It's not. Or they'll say it's amount of liquid or the amount of vapor over the amount of the total mixture of liquid and vapor. Well, amount needs to be like, really, what are we talking about? It's the mass. The mass and the mass. True? Not volume. It's not a volume fraction, it's a mass fraction. So if I have 50% if I have a container right here, and I say it's 50, the quality is 50%, and it's steam, all right? Can you tell me, and if I'm going to have gravity going this way, okay, so what's going to collect in the bottom of that container if gravity's down? The liquid, we understand that. So if I said the quality is 50%, will the liquid level be about that? Or will the liquid level be about there? Or will the liquid level be about there? And then what's above the liquid level? The vapor is above it. That's what's above the liquid in the container, right? So answer A, B, or C for a quality of 50%. I'm going to pause, walk around, see if you understand. All right, how many people, and all hands are going to go up because I'm going to ask a question where all people say, yes, that's me, want to eventually become a registered professional engineer? All hands go up. Right. Think about it. Is our society becoming more litigious? Yes. Do we have more licensing? Yes. Is it more important to be credentialed? Yes. So if you're going to practice in engineering, unless you decide to get a degree in engineering, then go into medicine or law or some other field, I recommend you get your engineering exam taken care of. The first exam, right after you graduate from an ABET accredited program, is the what exam? The FE exam. And I almost guarantee you this type of question will be on it, testing your knowledge of thermodynamics. It'll explore, do you understand quality? Can you answer a question about quality? Do you know what it means? Right? And so we should get that the A is the correct answer. One of the reasons that we know is liquid. Is it very dense at the same pressure and temperature compared to the vapor, or not as dense? What about liquid? You have to have some intuition. Liquid's dense, true. It doesn't take a lot of volume in order to hold a lot of mass. And if it's 50% by mass, liquid 50% by vapor, I better have a whole lot more volume of the vapor on top of the liquid. A lot more. Anybody remember roughly the ratio? Liquid to vapor. What's the density difference between the two? Yeah, it's over 1,000, typically around boiling point. You know, if you go lower pressures, it's even greater. So you ever remember as a little kid, you know, you're starting to learn the value of money. Hey, look I've got this big coin. It's a lot bigger than that little coin. I'll tell you what, I'll trade that penny for that dime. And you did a few of those trades, right? And then you've wised up and said, no. I don't want that. I don't want to make that trade anymore. Right? I give you a dime, you give me a penny. No, I don't want to do that anymore. Anyway, the water, if you wanted to throw a number out, it would be around 2,000. That's a lot of difference. For the same amount of mass, I need 2,000 times the volume for the vapor. Liquid, a lot smaller. Okay, now let's press forward. We're understanding this problem. The mass flow rate of the refrigerant's given. The refrigerant enters or exits at 30 degrees C. Well, if it came in at 26 and it exits at 30 degrees C, and there's no significant change in the pressure, how do you describe state 4 coming out? State 3 was two-phase saturated liquid vapor mixture. All right, so what about state 4? It is superheated vapor. It's true? All right, very good. Now, the first question, ignore the effects of gravity and motion. What did they say when they ignore the effects of motion and gravity? Negligible changes in kinetic energy and potential energy in our energy balance statement. It didn't say that it's not moving. It just says that it's negligible in the energy balance statement. So, first question is what is the rate of heat transfer, not from the refrigerant, but to the refrigerant stream. That means from. So basically, we know there's heat transfer from the hot into the cold. True? And they want to know what is this Q dot internal to the heat exchanger, which is out of the hot and into the cold fluid stream. The refrigerant is the cold fluid stream. So how do I calculate it? And here's the answer, 2732 kilojoules per hour. How do I calculate that? Okay, let me try somebody else. Okay, but you need to back it up. You're getting too detailed down into the forest. Or just do an energy balance for a very select control volume, which I clearly define. What is my clearly defined control volume? Pardon? Just only around the cold stream. So I could draw a control volume that's large like this, and sometimes we do. Sometimes I can draw a control volume which is simply around the cold fluid stream, because now for that smaller control volume I do have Q coming into it, and I only have one m dot in and one m dot out. All right, so if I write the first law for this control volume around the cold fluid stream, I can manipulate the equation in a few steps. I don't have a lot of space. You've done these problems before in Thermo 1. If you need to review and refresh your memory, absolutely do it. But you should get, after a little bit of work, the Q dot into the refrigerant is equal to the mass flow rate of the refrigerant times, let me ask this question. Question A or B? Is it going to be the internal energy exiting minus internal energy inlet? Or is it going to be the enthalpy exiting minus the enthalpy coming in? Either this option or that option. I'm going to pause, walk around. Do you understand my question? All right, so it's a difference in enthalpies, not a difference in internal energies. True? Now, you should know why that's true. Why is it H3 minus, H4 minus H3? Somebody want to give me their logic? Okay, you'll be the volunteer. And this is not a closed system. This is an open system indicated by a control volume, and the mass flow rate cuts across it. And so the flow work needs to be accounted for. And it's accounted for in the property enthalpy. Exactly right. All right, now let's press forward. This, how would I get these two enthalpies? One, I use for H3, I'm going to use the quality. I'm going to have H of the saturated liquid plus the quality at 3 times HFG. True or false? What is the name of HFG? The heat of, or latent heat of vaporization, going from saturated liquid to saturated vapor. All right. Now let's go to part B. You ready to press forward? You're not ready, but we got to do it anyway. What is the change in the flow exergy rate from inlet to exit for the refrigerant 134A stream? That's a long question. The part A was really easy. I'm just looking for Q dot. But there's really not a nice, easy little package symbol for what the answer should be for part B. Sometimes it's P. You're looking for pressure. Sometimes it's T. You're looking for temperature. Sometimes it's W dot. You're looking for power. Sometimes it's Q dot. But what symbol are we really looking for? Change in the flow exergy rate from inlet to exit for part B. We're looking for the product of the mass flow rate of that cold fluid. I left that subscript off right there, but I think you knew it. Times EF4 minus EF3. Isn't that what we're looking for? Yeah, it's how did that fluid stream's flow exergy change? Did it go up or down? Which way is it going to go? Is it going to increase or decrease? The cold fluid stream, does it come out higher flow exergy than inlet? So it was an increase, true? An increase. So how do I calculate that? Because it's a rate, and look at the units on this, kilojoules per hour. That's how much, at steady state, that's how much there's an increase in the fluid stream's exergy. All right. So we know the mass flow rate or not mass flow rate? Yeah, we do. It's right here, 30 kilograms per hour. All right. How do I calculate this change in the flow exergy? That's exactly right. H4 minus H3 minus T naught times S4 minus S3. It's just a property, remember? The flow exergy was a property. The difference of flow exergies is these are simpler. And we didn't write down the KE4 and KE3 because they told us negligible changes in the kinetic energy as well as potential energy. So you have to be able to get the property enthalpy as well as entropy at state 3 and 4. All right. Ready for next part? Let's go to the next part. What is the rate that exergy is being destroyed in the heat exchanger? There is a nice simple symbol for that. Isn't that what we're asked to calculate? E dot D? What's the units? Does that look reasonable? So many kilojoules per hour? Exergy destruction rate? I want to pause, walk around. I'm going to run out of time. But I want you to solve the problem. Can you tell me? To speed me up, you call me over and I'll check your work. I get 3 correct answers. We move on. Give me the equation. All right, so what do we do is a lot of people said, look, I know the dead state temperature. If I just get the entropy production rate due to irreversibilities, I can get the exergy destruction rate. There it is. There's another way of doing it, exergy balance. 2 ways of doing it. This may be easy. Do it one way, fine. Or you could also do an exergy balance. If I get what comes out of the hot, and I already calculated what went into the cold for exergy flow rates, what is the difference? The destruction. Do we have some exergy flowing out of the hot? Yeah, absolutely. How will we calculate? Just like we calculated what into the cold. M dot hot times EF1 minus EF2. So either one will work. Here is the answer for part C. How about answer part D now? What is an exergetic efficiency? Notice that the answer is only about 17%. Right? Your football coach says, go out there and give it all you got on the field. Go give it your 17%. You're not going to be too excited. Right? That's not a really high percent. But how would you calculate this nearly 17% exergetic efficiency? If you already calculated what was destroyed, then you could use this equation to get what comes out of the hot, couldn't you? And so the exergetic efficiency is, hey, a lot came out of the hot, but did all of it go into the cold? Nope. But this much did go into the cold. So you could use your exergy destruction rate and calculate then what went out of the hot fluid. Then calculate the exergetic efficiency. In the interest of time, I want to try to get to another problem. Is that fine? You got it? Let's move on. Steam flows adiabatically through a nozzle. Are you familiar with a nozzle? What's the shape of a nozzle that you solved in Thermo 1? It's like this. So if I look at it, I have some cross-sectional area. I know that's not drawn very well. A lot of people want to draw like this, right? There's an image of a cross-sectional area, right? Okay. So what about this area coming in versus the area exit for a nozzle? One's big and one's small. That's big and it's small. So that's what's happening is your flow's coming in, going out. State 1, it's slower. The purpose of the nozzle is to get the speed at 2 much, much greater than the speed at 1. True or false? That's the purpose of a nozzle. All right, so they tell us things like the pressure in, the pressure out. What does the pressure do going through a nozzle? Pressure go up, down, stay the same? Nozzle, nozzle, nozzle. Pressure is going to go down, isn't it? You have to think through. You have to think through. Sorry about that. I asked you questions. Thank you for participating. But even sometimes I'll ask a question and I'll even stumble on the answer. So don't be embarrassed if you get something wrong. All right, here's T. What about the temperature? That one's a little harder. It's actually a lot harder. But typically, the temperature is going to go down. The pressure goes down. Typically. Not always. All right. So how do I do this? I think I look at all the information given. They give us the speed coming in, 75 meters per second. They give us the temperature coming in, 600. They give us the pressure coming in, 6 megapascal. It's steam, so it's water vapor, it's steam. And then the pressure and the temperature, they tell us dead state temperature and dead state pressure, ignore effects of gravity. And then for part A, steady state operation, what is that exit velocity V2? How do I find that exit velocity V2? How do I find that exit velocity V2? Okay, can you write it down correctly? Somebody said you would do an energy balance to calculate it. Can you write down the energy balance correctly and show me in a, not necessarily one final equation, but maybe this equation followed by that equation, 2 or 3 equations, and there's the answer. Can you do that? I'm going to pause, walk around. All right, little quick review of Thermo 1. We do a control volume, clearly defined. We only have one inlet, one outlet. Do we have any heat transfer in or out of that control volume? Do we have any shaft work in or out of that control volume? Is it flowing at steady state? Yes. So anyway, you have no heat transfer, no work transfer. One mass in, one mass out. Basically, the conservation of energy, the energy balance gives us that the inlet enthalpy plus the inlet kinetic energy is equal to the exit enthalpy and the exit kinetic energy. Wow, it seems like another equation I can memorize for the exams. Don't memorize it. Be able to rederive it quickly. Right? So you go and you know the conditions of the steam by the pressure and temperature. I can get inlet enthalpy. You know the pressure and the temperature. I can get the exit enthalpy. I know the speed coming in. Can I get the kinetic energy coming in based on the speed? What is that equation? 1/2 V1 squared. There's a difference between this KE and that KE. What's the difference between the two? Uppercase, lowercase. What does uppercase, lowercase? What's the difference between the two? Per unit mass, specific kinetic energy. There's a difference between cap H and lowercase h. What is the difference? Total enthalpy or specific enthalpy? Same thing, right? So is this the correct equation for the specific kinetic energy? 1/2 V squared. Professor, where's the M? It's specific kinetic energy, right? You divided that out. So if I run this, let's do this one. Let me get to the right sheet here. I'll give you some numbers. And then if you have a calculator, I just think we just may have enough time. So the enthalpy coming in is 3658.4 kilojoules per kilogram. The speed coming in is 75 meters per second. The exit enthalpy, knowing the temperature and pressure, is 3536.9 kilojoules per kilogram. Calculate KE2 for me. And then once you calculate KE2, if we know that that's also equal to 1/2 V2 squared, then V2 is equal to 2 times the KE2 square root. True or false? So I want you to calculate both the KE2, the specific kinetic energy at the exit, as well as then the velocity at the exit. Please do that. I want 3 right answers. You'll need a calculator. All right. So when you calculate this kinetic energy 2, right? What did you get? Did you get 124? Oh yeah, like yes or no? It is correct, okay, but how did you calculate that? That KE2 is 124.31 kilojoules per kilogram. The big unit conversion that a lot of people will miss is that when you do a meter per second and you square it, does that immediately convert to a kilojoule per kilogram? No, it's not a 1-for-1. You need 1,000 meters squared per second squared. That's precisely equal to 1 kilojoule per kilogram. This is what we call unit conversion factor. I saw a number of people had it in their equations, which is good. All right? So you'll get some numbers. You can't tell if they're right or wrong, but if you don't have the right unit conversion in there, the numbers will give the wrong answer. So this kinetic energy is 124.3, and then the speed comes out to be around 498.6 meters per second. I have 2 minutes. What's the answer for the rate of Exegy destruction? How would I calculate the rate of Exegy destruction? Would I do the dead state times rate of entropy production? It's a pretty good strategy. Can you do an entropy balance and get the rate of entropy production? Is that the mass flow rate times S2 minus S1? Just like you got the H's out of the tables, you get the S's out of the tables. And then you can calculate 34.1 kilowatts for the rate of Exegy destruction. Thank you very much for your attention.